Welcome to the Deep Dive, where we try to cut through the noise and get to the core insights behind new developments. Today, we're taking a deep dive into a really interesting paper. It's titled Group Sequence Policy Optimization, and it seems to unveil quite a significant breakthrough in how large language models are trained. Now, you've probably seen what these advanced language models can do. I mean, solving complex math, writing code, having pretty nuanced conversations. But how do they get so smart? Especially for those really sophisticated tasks that need deep reasoning. A big piece of that puzzle often involves reinforcement learning, or RL.
That's right. RL is really essential for giving models these advanced skills. But scaling it up, especially for the truly massive models we have now, has hit a major roadblock. The core challenge is keeping the training dynamics stable and, well, robust. And this paper points out that the existing state-of-the-art RL algorithms, like one called GRPO, often show really severe stability issues, can lead to what the researchers call catastrophic and irreversible model collapse.
Wow.
Okay. Yeah, and this isn't just a small glitch. It's seriously hindered efforts to, push the boundaries of what these models can actually do.
Okay, let's unpack this a bit. Our mission for this deep dive is to really get a handle on this fundamental stability problem, understand why it happens, and then explore how this new method, Group Sequence Policy Optimization, or GSPO, directly addresses it. We want to see how it offers a more stable, maybe more efficient, and ultimately better way to train these powerful AI systems. We'll look at why it's different and, what that really means.
To really get GSPO, we first need to understand the challenge it's solving. So reinforcement learning lets models learn complex stuff by getting rewards for their answers. Like you give it a coding problem, it writes some code, and then gets a reward based on whether the code works, how efficient it is, that sort of thing.
Makes sense.
But as the models get bigger and the answers to sequences get longer, just keeping that training process stable becomes incredibly hard.
You mentioned GRPO earlier as a key example of current methods. The paper says the instability there comes from misapplying importance sampling weights. Can you maybe break that down a bit? What are those weights?
Sure. So in RL, models learn by trying things out. But constantly generating brand new data for every single learning update is super inefficient. So
Right.
what researchers do is reuse data from older interactions, even if a slightly older version of the model generated that data.
Ah, okay. Like recycling training data.
Sort of, yeah. Importance sampling weights are basically a mathematical way to adjust for the fact that the old data wasn't generated by the exact same policy the model is learning right now. They tell the model how relevant that old data still is. It helps correct for the slight mismatch, allowing what's called off-policy learning.
Okay, so they're important for efficiency, but how does GRPO mess them up?
Well, the critical issue with GRPO, according to the paper, is that it applies these weights at the token level.
Token level. So
Yeah.
for each individual word or part of a word.
That's right. In a long response, GRPO tries to adjust the learning signal for every single token. The problem is these token-level weights, based on just one sample usually, introduce a lot of high-variance noise. It's very unstable.
So like trying to steer a ship by adjusting thousands of tiny flapping sails instead of the main rudder.
That's a pretty good analogy, actually. This noise builds up over long sequences. And somewhat counterintuitively, the clipping mechanism, which is supposed to prevent updates from going haywire, actually makes it worse in GRPO's case. It amplifies the noise. Ultimately, this can cause the whole learning process to just collapse. The key insight they missed, the paper argues, is that the unit of optimization objective should match the unit of reward,
Meaning?
meaning the reward is given for the entire response, the whole sequence. So trying to make corrections at the tiny token level was mismatched and problematic.
Right. So this isn't just a minor bug fix needed. It sounds like a fundamental flaw in the design. What does catastrophic and irreversible model collapse actually mean for the people training these models? Is it just wasted time and money?
It's definitely wasted time and money, which is significant, but it's often worse than that. Imagine spending weeks or months and potentially millions in compute costs training a huge model only for its performance to suddenly nosedive. It starts generating nonsense, becomes unusable.
And irreversible means you can't just tweak it back.
Generally, no. The learning state gets so corrupted that often the entire training run has to be abandoned. You have to start over. It's a massive setback.
That sounds incredibly frustrating and like a real barrier. So how did they get around this? This brings us to GSPO. This is where it gets really interesting, right? They proposed redefining this importance ratio, but how?
They shifted the focus entirely. Instead of looking at individual tokens, GSPO calculates the importance ratio based on the likelihood of the entire sequence.
The whole response.
The whole response. It measures how much the entire generated sequence deviates from the model's current policy. This naturally aligns with the reward, which is also given for the entire sequence. And crucially, the clipping is also done at the sequence level.
Ah, so instead of clipping noisy token weights.
Right, GSPO looks at the whole sequence's importance ratio. If the entire sequence is too off policy or looks too strange compared to what the current model would generate, it simply excludes that whole sequence from the gradient update.
So it throws out the whole problematic example instead of trying to fix bits of it.
Essentially, yes. It provides a much cleaner, more stable learning signal by focusing on the reliability of the whole sample.
The paper also mentions length normalization applied to this sequence level ratio. Why is that important?
That's another clever part.
Yeah.
Sequence likelihoods can naturally vary a lot just based on the length of the sequence. A very long sequence might have a tiny likelihood just because it's long. Length normalization adjusts for this, making the importance ratio less sensitive to just the raw length of the response.
Okay, so it prevents long sequences from having disproportionately weird importance values.
Exactly. It helps reduce variance further and keeps the values in a more consistent numerical range, preventing big swings caused by small changes in long responses. And importantly, unlike GRPO, which weighted tokens differently, GSPO weights all tokens within a chosen sequence equally when calculating the gradient update. This removes another big source of instability.
I see. And there was a variant mentioned, GSPO token?
Yes, GSPO token. It's a variation that allows for a bit more fine-grained adjustment of advantages, which can be useful in specific settings like multi-turn conversations, but it still builds on the core stable foundation of the sequence-level ratio and clipping. The theory sounds good, but the proof is really in the pudding, right? The empirical results are where GSPO really shines. The experiments show pretty clearly that GSPO leads to better training stability, it's more efficient, and achieves higher overall performance compared to GRPO.
And you mentioned this translates to real gains. The paper said GSPO allows for continuous performance improvement with more compute.
That's a key finding. It means as you invest more computational resources, the model actually keeps getting better, which wasn't always happening reliably with GRPO due to the instability.
And better benchmark scores, too, on things like AIM, Live Code Bench.
Yes, across several challenging benchmarks, GSPO achieved better results. And the kicker, as you said earlier, is that it did this using the same amount of training compute as GRPO runs that often collapsed or plateaued.
So, better results, same cost. That's compelling.
It really is. And it leads to one of the most interesting findings, actually. GSPO ends up clipping or discarding a much, much larger fraction of tokens during training than GRPO does, like 2 orders of magnitude more.
Wait, it throws away more data but learns better? That seems backwards.
It does seem counterintuitive at first glance. But what it strongly suggests is that GRPO's token-level gradients were just so noisy and unreliable that trying to learn from them, even though it used more of the data, was less effective than GSPO's approach of only using the more reliable whole sequence signals, even if that meant discarding entire sequences.
So quality over quantity for the learning signal.
Precisely. GSPO's sequence-level signal, despite discarding more raw token data, provides a much more effective path for the model to learn.
Now, beyond general LLM training, the paper highlights specific benefits for a mixture of experts models, MoEs. These are super powerful, but also known for being tricky to train, right?
Extremely tricky, especially with RL. MoMI models have this issue called expert activation volatility.
Okay, what's that?
Think of a MoE like a big company with many specialist departments, or experts. For any given task, only relevant experts are activated. The volatility issue is that with methods like GRPO, the set of experts chosen for the exact same input can change drastically after just 1 or 2 learning steps.
Ah, so the team working on the problem keeps changing unpredictably.
Exactly. The paper mentions that for a large Qwen 3 model, maybe 10% of the activated experts could be different for the same input after just a couple of updates. This constant shifting completely undermines GRPO's token-level importance calculations because the underlying machinery producing the tokens keeps changing. It makes stable convergence very hard.
And didn't they need a complex workaround for this with GRPO? Something called routing replay?
Yes, routing replay was developed. It basically involved remembering which experts were used by the old policy that generated the data and forcing the model to use those same experts during the learning update.
Kind of like freezing the team assignment artificially?
In a sense, yes. It helped GRPO converge by forcing stability, but it had downsides. It needed extra memory, more communication overhead to store and pass around that routing info, and potentially it limited the model's ability to learn the best expert routing dynamically. It was a crutch.
So how does GSPO help here?
This is one of the most elegant benefits. GSPO eliminates the need for routing replay entirely, because GSPO stability comes from the sequence-level likelihood, which is much less sensitive to which specific experts fired for which specific tokens. It isn't thrown off by this expert volatility.
It doesn't care as much about the micro-level changes.
Right. It focuses on the overall output sequence probability. So GSPO inherently handles the expert volatility problem, allowing MOE models to train stably with RL without needing complex, potentially limiting workarounds. It lets the MOE learn more naturally.
That sounds like a huge simplification and potentially unlocks more performance from OEs. And there was one more benefit mentioned regarding the training infrastructure itself. Something about precision differences between training and inference engines.
Yes, that's another practical advantage. Often, the software engine used for fast inference during data generation might have slightly different numerical precision than the engine used for the actual training updates.
Oh.
With methods sensitive to token-level details, this often forces you to recompute the likelihoods of the generated sequences using the more precise and usually slower training engine, just to be safe. It's an extra costly step.
Another bottleneck.
Definitely. But because GSPO relies on the sequence-level likelihood, which is generally more robust to these small precision differences, it opens the door to potentially directly using the likelihoods calculated by the faster inference engine.
Ah, so you skip the recomputation step.
Potentially, yes. This could significantly simplify the RL training pipeline, saving time and compute, especially in more complex setups like partial rollouts or where training and inference systems are separate. It's a practical engineering benefit that stems directly from the algorithmic design.
Okay, so let's try and wrap this up. We've covered quite a bit about Group Sequence Policy Optimization, GSPO. It seems like a new RL algorithm that tackles fundamental stability issues in training large models by shifting the focus from individual tokens to the entire sequence likelihood.
That's the core idea. And the result is significantly better training stability, higher efficiency, and ultimately better model performance compared to prior methods like GRPO. Its impact seems especially strong for training those complex, large-scale mixture of experts models.
And the paper directly links these improvements to the progress seen in models like the recent Qwen 3 series. It really shows how these foundational algorithm changes can unlock new potential in RL for LLMs.
It absolutely does. It underscores how sometimes seemingly technical shifts deep within the algorithms can have really profound effects on the capabilities and reliability of the most advanced AI systems we're developing.
It makes you wonder, doesn't it? So here's a thought to leave you with. As researchers continue to make these kinds of fundamental improvements in algorithmic stability and learning efficiency, what new kinds of complex reasoning or intelligent behaviors might this unlock in the next wave of large language models that you'll interact with?